Okay, so we designed this in SolidWorks, and rather than doing a 4-bar linkage, we decided to do a spool a spool and pulley system, which you can see here. We calculated the diameter of the spool such that it would give positive and negative 10 degrees of incline, so the ball will have up to 10 degrees of incline to cause it to roll one way or the other. We thought this would be enough to give it enough speed, but also would be a good limit. We wouldn't really want to go more than that. All the pieces were made on the laser cutter besides for the spool, and we made these tick marks here, 1-inch increments, which will be able to tell where the ball is later on.
The black piece that controls the string and the spool was made on the lathe. It was cut from a piece of 3-inch Delrin stock, and it was turned down to 2.56 inches exactly. It has a groove cut into it, and it was parted off so that it's just over 1/4 inch. And then it was then screwed into so that the servo could spin it as it goes.
We also made this tail on the edge rather than, since there only needs to be 12 inches of pivot, we decided to make the tail on the end to support the strip so we didn't get any false location readings of the ball.
Should be good, I think. Okay, so this is our Arduino code. As you can see, the Arduino code's on the left and the output window is on the right. The left side is the potentiometer on the ball balance that shows position in inches from the reference point, which is right here. The potentiometer, the right side is the potentiometer that's the reference point. So as you see, we have a little dial here. It's set to 6 right now. So if you take a look at our code, it's displaying 6.11, and it is set to 6. As I change it to 8, it's now reading 8.13. Same as the ball balance, it's right now at position 3, and it's reading 2.95. If Hoagie moves his finger to 6 on the ball balance, it should change to just about 6, 5.81.
All right, so in order to model the ball balance as a second order system, you can zoom on in over here to our set of equations. So here you will see a free body diagram of the system as a whole. So this is essentially the beam that you can see up, just pan over. If you see up there, and then we're obviously pinned at this point, which is the pivot point of the actual beam itself. And then we are also secured here on the string, which if we come over here, that represents that there. And then we have our pulley up here, which is pinned to the ground. So in order to represent this system, we have L, we define L as the length of the beam, X as the ball's distance from the furthest end of the beam, theta is the angle that the beam is from the horizontal, and then we also define X to the left as positive, and we also define the radius of the pulley and the angle of the pulley itself as alpha. So moving down further, we can model the whole system by just looking at the ball. So here is a free body diagram of the ball itself. We have lowercase r as the radius of the ball, phi as the angle that the ball is moved, F centrifugal force that pushes the ball upwards due to the rotation of the beam itself, force of friction opposing the motion of the ball, assuming it's moving down the ramp, and force of gravity that would be pulling the ball down as it's moving down the ramp. So in order to fully define a system, we need to define each force. So from simple gravitational calculations, we can deduce that the force from gravity is mg sine theta. The centrifugal force, we actually get this final answer from the definition or the relationship between linear velocity and rotational velocity. So the equation for that is mv squared over r, which we can manipulate to mr omega squared. And again, that's about the beam because that's the force due to the beam itself rotating. So here we can define centrifugal force as F sub c equals m times L minus x theta dot squared. And then the last force that we need to find here is the force due to friction, and we can figure that out by summing the torques about the ball. So you have J phi double dot is F friction force times radius. And then from here, we know that phi, which again, we defined phi as the angle that the ball has rotated, as x over r, meaning the distance that the ball has moved from the end of the beam divided by the radius of the spherical ball. And then obviously from there, we can get phi dot as x dot over r and phi double dot as x double dot over r. So from all of this, we can deduce that our force of friction is J over r squared times x double dot. Now finally, we can sum all these forces up to model our system and obtain the governing equation. So from here we see mx double dot equals force of gravity minus force of friction minus the centrifugal force. So moving forward, we're just plugging in all of our forces here, and then we eventually arrive at this equation here, and then we can sub in J is 2 over 5 mr squared, and then again plugging that forward, we can arrive here, and then I believe, yes, the masses all cancel out, so then we come down here, 7/5 x double dot plus L minus x theta dot squared equals g sine theta. And now from here we have a few assumptions. We can assume small angle assumption because our beam is only expected to move plus or minus 10 degrees. We can assume that the sine of the theta angle is approximately equal to theta. And then we can also assume that the velocity at which this beam is moving angularly is very small. So we can approximate it to be 0. And then from there, essentially this middle term cancels out because theta dot is 0, and sine theta becomes theta. So our final equation becomes 7/5 x double dot equals g theta. And if we come over to the final page, we have one more assumption, because actually we need to relate the equation that we just got, where in terms of x and theta, we want to just get it, we essentially need to relate the beam to the pulley rotation and account for the servo motor. So from here, we can assume that r alpha, which again we equated alpha to the angle of the pulley itself, we can set r alpha approximately equal to L theta. And then from here, our final equation becomes 7/5 x double dot equals rg alpha over L.